Applications of the Sieve formula. Let us discuss some classical applications of the Sieve formula. The first is the problem of derangements. Example 7.4. A party was attended by n guests. When the guests arrived, they left their hats in the same courtroom. After the party ended, there was an electric power failure, so each guest took a hat from the courtroom at random. When the guests were back on the street, they were amused to find out that none of them got his hat back. In how many different ways could that happen? In a more mathematical formulation, how many permutations of the set n braces have no fixed points, that is, have the element I in the ith position for no I? Such permutations are called derangements. Indeed, if the hat of the first person is denoted by 1, that of the second person is denoted by 2, and so on, then every way of the n people taking the n hats corresponds to a permutation of the set n braces. If the first person takes hat 7, then the first element of this permutation will be 7. If the second person takes hat 3, then the second element of this permutation will be 3, and so on. Now that we showed that the two formulations are in fact equivalent, we will give our answer in the language of permutations. Solution of example 7.4. It is easy to count permutations in which entry 1 or entry 2 or entry I is not a fixed point, but we want permutations with no fixed points. Their number is clearly equal to the number of all permutations minus the number of permutations with at least one fixed point. This sounds similar to the two examples we have discussed at the beginning of this section. Let AI be the set of all permutations of n braces in which the element I is in the ith position, in other words, in which the element I is fixed. Then theorem 7.3 will give us the answer to our question if we can compute the sizes of the intersections on the right-hand side of 7.1. What is the size of A1? The set A1 consists of permutations in which the first element is 1. This means that elements 2, 3, 4 until n can be freely permuted among each other, and this can be done in n-1 factorial different ways. So the size of A1 is equals to n-1 factorial. Similarly, the size of A2 is equals to n-1 factorial, as in the case element 2 has to be fixed, and all the remaining elements can be freely permuted. Similar argument showed that the size of AI is equals to n-1 factorial for all n values I in n braces. Therefore, the total contribution of the first term of the right-hand side to the total value of the right-hand side is n-1 factorial times n, which is equals to n factorial. Now we move up to the next member of the right-hand side of 7.1. That is two intersections of the type. The size AI intersect AJ. The set AI intersect AJ consists of permutations in which elements I and j are fixed, and the remaining n-2 entries can be permuted freely in n-2 factorial ways. As there are n choose 2 choices for I and j, the total contribution of the second term is minus n choose 2 times n-2 factorial, which is equals to minus n factorial times n-2 factorial divided by 2 factorial times n-2 factorial, which is equals to minus n factorial divided by 2 factorial. In general, similar argument shows that the contribution of the ith term is minus 1 to the I minus 1 times n choose I times n minus I factorial, which is equals to minus 1 to the I minus 1 times n factorial divided by I factorial times n minus 1 factorial, then times n minus I factorial. So after simplification, it becomes minus 1 to the I minus 1 times n factorial divided by I factorial. Indeed, if I given elements are fixed, the remaining n minus I elements can be permuted in n minus I factorial ways. On the other hand, there are n choose I possibilities for the set of I given elements. Therefore, theorem 7.3 yields the size of A1 union A2 and so on union AN, which is equals to the doubling summation, with the outer summation summing for the term minus 1 to the j minus 1, with j starting from 1 to n, and the inner summation summing the size of AI1 intersect AI2 intersect AI3 and so on intersect AIJ, summing with the I1, I2, I3 until IJ, which is equals to n factorial minus n factorial divided by 2 factorial plus n factorial divided by 3 factorial minus n factorial divided by 4 factorial and so on, plus the last term, which is minus 1 to the n minus 1 times n factorial divided by n factorial. So the general formula of such a summation is the summations of minus 1 to the I minus 1 times n factorial divided by I factorial, where the summation is with index I starting from 1 to n. So we have computed the number of permutations of n braces with at least one fixed point. Consequently, the number dn of permutations of n braces with no fixed points, or the number of derangements, is n factorial minus this number. That is, d of n is equals to the summations of minus 1 to the I times n factorial divided by I factorial, summing with index I starting from 0 to n, and this completes the proof. The right-hand side of formula 7.3 strongly depends on n. Still, the reader may want to get a feeling about roughly how likely it is that a random permutation has no fixed point. One can get such an intuition by dividing the number of favorable outcomes by that of all outcomes, that is, dividing the number of all derangements of n braces by that of all permutations of n braces. This yields d of n, the derangement number of n, divided by n factorial, which is equal to the summations of minus 1 to the I times 1 divided by I factorial, summing with I starting from 0 to n, which is equal to the summations of minus 1 to the I divided by I factorial, summing with I starting from 0 to n. This shows that if n converges to infinity, then d of n divided by n factorial converges to e to the minus 1. So for large values of n, roughly 1 over e, so more than 1/3 of all permutations are derangements. So there is a fairly high chance all people will be looking for their hats. We have promised in section 5.2 that we will obtain a formula for the Stirling numbers of the second kind. Time has come to fulfill that promise. Theorem 7.5. For all positive integers n and k, the equality S of nk, which is equals to 1 over k factorial times the summations of minus 1 to the I times k choose I times k minus I to the n, summing with index I starting from 0 to k, which is equals to the summations of minus 1 to the I times 1 over I factorial times k minus I factorial times k minus I to the n, summing with index I starting from 0 to k holds. Proof: instead of finding a formula for S and k, we will find a formula for k factorial times S of nk. We know from corollary 5.9 that the latter is the number of all surjections from n braces to k braces. It is clear that the number of all functions from n braces to k braces is k to the n, as any element of the domain can be mapped into one of k elements. However, not all these functions will be surjections. Many will miss one, two, or more elements of k braces in their image. We have to enumerate these that do not miss any element of k. This sounds a little bit similar to the previous problem. We were also interested in the number of a certain object, n0, part of which had a certain property. It is therefore hopeful that the same approach will work here. Let I in k braces and let ai denote the set of all functions from n braces to k braces whose image does not contain I. It is then clear that the size of ai is equal to k minus 1 to the n, as such functions can map any element of n braces into any one of k minus 1 elements. Similarly, the size of AI1 intersect AI2 intersect AI3 intersect Aij is equals to k minus j to the n for all j which is less than or equals to k. Therefore, the Sieve formula yields the size of A1 union A2 union A3 and so on union AN is equal to the summations, doubling summations with outer summation summing with term minus 1 to the j minus 1, summing with j starting from 1 to n, times the inner summation summing with the size of AI1 intersect AI2 and so on intersect Aij, summing with all terms I1, I2, I3 until Ij. Where we combine the both summation, we get one single summation, summing the term, summing minus 1 to the I minus 1 times k choose I times k minus I to the n, summing with index I starting from 1 to k. This is the number of functions from n braces to k braces whose range is not the entire set k braces. So the number of those with range k braces, in other words, the number of surjections, can be obtained by subtracting this number from that of all functions from n braces to k braces, and our claim follows. The following theorem is just a version of the Sieve formula. We state it separately as its formulation goes in a direction we will continue in Chapter 16. Theorem 7.6. Let f and g be functions that are defined on the subsets of n braces and whose range is the set of real numbers. Let us assume that f and g are connected by g of s, which is equals to the summations of f of t, summing for all t which is subset equals to s. Then f of s is equals to the summations of g of t times minus 1 to the size of s minus t, summing for all t which is subset equals to s. Proof: if we express g of t by value of f on the right hand side of the equation to be proved, we see that for all t, the value f of t will appear exactly the summations of minus 1 to the I times the size of s minus I, choose I, summing with index I starting from 0 to the size of s minus t, which is equals to 1 minus 1 to the size of s minus t times. This number is always 0, except that the size of s minus t is equals to 0, that is when s is equals to t. So the only term on the right hand side that does not cancel out will be f of s, and the claim is proved. Note that we pointed out that the Sieve formula is often called the principle of inclusion-exclusion.